Hello, it's Dr. Daystorms, and we're starting a new chapter going over gases and the different properties of gases, and today we're first going to start discussing the characteristics of gases and ultimately leading up to what's called the ideal gas law. So the goals for today is to go over pressure and the units for pressure, to go over the individual gas laws and how that they ultimately come together to form what's called the ideal gas law. And this is one that you must memorize on your own. I won't provide you the equation for this, but it's one that's actually fairly simple to remember because of the mnemonic device that you can use. So first, let's just think about what makes a gas and how that they're different than liquids and solids. A solid is solid because of the fact that the interaction between the different molecules or compounds in it are really strong. They're tightly held together. A liquid, though, is a little less tightly together, and then we have the gas where the intermolecular bonds is little to none. Okay, so unlike liquids and solids, you're going to have a gas that will expand to fill the entire container that it's in. So what I mean by that is you can imagine if we had, let's change this. If we had, you can have a glass and fill it half full of a liquid, like water. However, if you took that same glass and you tried to fill it full of steam, which is water in the vapor or the gaseous form, it's just going to immediately escape, okay? Because there's no lid on that container. If it was a closed container, it would actually go to fill the entire container. You couldn't get a half of a glass full of a gas. Gases are highly compressible. It's hard to put enough pressure on a solid to get it to squish down. You can put some pressure on the liquid, but gases are highly compressible. Gases have extremely low densities, which is the reason why they float and easily escape. So now we're going to talk about pressure. And by definition, pressure is the amount of force that you apply over a given area. Which this figure here it's looking at the air pressure. And so that's the amount of pressure that's due to the gravity, okay, pressing down on any particular area. And so you can imagine that the atmospheric pressure is just literally the weight of the air per unit area. So some of the units of pressure that we use, one is the Pascal, where 1 Pascal is equal to 1 Newton of force per meter squared. Another one that's often used is a bar, where 1 bar is equal to 100,000 pascals. But sometimes these units aren't quite as easy to use, or may not be quite as common. Another one, this should be millimeters of mercury, Hg, which I didn't catch that, but H, it should be millimeters of mercury. Okay, which 1 millimeter of mercury is equal to 1 torr. Okay, and we are literally talking about millimeters in height, and the way that they do this is literally the difference. They just used to have a tub that had mercury in it, and then the amount of pressure would cause the mercury to go up a vacuumed column. Okay, and so they would measure this height, and 760 millimeters is equal to what they call 1 atmosphere. 1 atmosphere is the standard unit that we use here, because that's literally the air pressure, or the atmospheric pressure at sea level, and it's equal to 760 torr, which is also equal to 760 millimeters of mercury in the old-fashioned barometer. Okay, another instrument that gets used is called a manometer. A manometer measures the difference in pressure between the atmospheric pressure and a pressure that is in that gas vessel. So here what we are seeing is you've got gas, in a vessel, you fill it with mercury, or put some mercury in it. So that what happens is the gas is going to be pushing down on one end, from one end, while the atmospheric pressure pushes on the other end. So with manometer, the way to figure out the pressure of the gas is going to be equal to the pressure, atmospheric pressure, plus whatever the height is, the difference in the levels of the mercury. Standard pressure is, by definition, the normal atmospheric pressure at sea level, which here in Florida, we're right around sea level, and so almost always our standard pressure, almost always our atmospheric pressure is at standard pressure, and so typically we're right around 1.00 atm. And it should be noted that this is a precise number, that 1 atm is equal to 760 torr. So you don't have to worry about the 760 for significant figures. Likewise, 1 atm is equal to 101,325 pascals, or 101.325 kilopascals. Now, in this field of chemistry, in general chemistry, we have what we call the standard temperature and pressure, and the standard temperature is 0 degrees Celsius and 1 atm pressure. And so if we're under those standard conditions, that's what we're talking about. What you'll find out is in other fields, for example in biochemistry, it's very different, because standard temperature is not going to be 0 degrees Celsius, it's 37 degrees Celsius, since that's body temperature. Now we're going to get into the laws, the gas laws. And Boyle's law is actually something that's fairly simple when you think about it. What it states is that the volume of a gas, and it's a fixed amount of gas, so the amount of gas is not changing, and we keep the temperature constant. And so what it is the volume is inversely proportional to the pressure. So therefore, if you add a lot of pressure, then the volume is going to decrease. So as pressure increases, the volume decreases. As pressure decreases, the volume can increase. Okay, so they are inversely proportional. Mathematically, the way that we say inversely proportional is you'd have to say that the volume times the pressure has to equal some type of constant. Okay, so that's the reason why as volume increases, the pressure has to decrease, or vice versa. So we can plot this mathematically. So if you plotted volume as a function of pressure, as the pressure increases, the volume, we can see, decreases. See, the volume goes down. And if we do what's called a reciprocal plot, then it actually forms a line with the slope, and the slope is actually equal to k. Okay, so we can see this because if we plot volume as a function of 1 over pressure, you get a straight line. But the take-home message is they're inversely proportional. If the volume increases, the pressure is decreasing. If the pressure increases, the volume decreases. You can compress a gas. Charles' law is also something that's fairly simple to think about. What it says is that if you have a fixed amount of gas, and once again, now the amount's not changing, and here the pressure isn't changing, then it's going to be directly proportional to the temperature. So if you think about it, what that's saying is that if you heat a gas up, so think about what happens as you boil water. After you add more and more heat, the volume is going to increase and get bigger and bigger and bigger. See, it's relatively simple. And so what happens here is if you plot volume as a function of temperature, you get a straight line. Okay, and so that's where they get this idea that the volume divided by temperature has to equal some fixed constant. Because as temperature increases, volume has to increase by the same amount. Okay. Next up is called Avogadro's Law. And we remember Avogadro from the whole idea of Avogadro's constant and what the amount of items that's in a mole. Well, this is where what happens is if you keep temperature and pressure constant, then the volume is going to be directly proportional to how many moles of gas you have, which should make sense. As you add in more number of moles of gas, the volume's going to get bigger and bigger and bigger if we don't do anything to change the pressure or to change the temperature. Okay, so the volume is going to increase as we go along by adding more and more gas. So let's work a thought problem here. This is just a logic problem. Okay, here let's decide what happens to the density of a gas. And in the first scenario, we're going to have the gas heated in a constant volume container. So what does that mean? We have a container, it's got a lid on it, so we don't have to worry about the gas escaping. So we have gas in there. The volume isn't changing, but we're starting to heat it up. So you've got your flame. So the flame is heating it up. So what's happening to the density of the gas? Well, first off, let's write out what density is. Remember, density is equal to mass divided by volume. Well, the mass of the gas does not change as you heat it up. And since this is a constant volume container in part A, the volume isn't changing either. So that means that for the answer for part A is that there would be no change. Density does not change as you heat a gas up in a constant volume container. Okay? Now, let's see about part B. In part B, it says if the gas is compressed at a constant temperature. Now we leave the temperature the same, but what does this mean? We have our container, it's full of gas. Now what's going to happen is I'm going to draw like a piston, and this piston has now been shoved down. Whoops, let me do a different color. We're shoving it down. Once again, remember, density is equal to mass divided by volume. The mass doesn't change, but what's happening to the volume? That's right, the volume is decreasing. So if we take a number on the top, the mass, there's no change. NC for no change. And you're dividing it by the volume, which is decreasing. That means you're taking a number up here that has no change, and this number is getting smaller. That means that density is increasing. So density increases if the temperature remains the same and the gas is being compressed. Finally, let's say that we're adding additional gas in a constant volume container. So we need to draw our container. So the containers, the volume staying the same, the temperature presumably staying the same. The only thing that's changing is we keep adding more gas into this. Well, now we have density is equal to mass over volume. It's this number on top that's getting bigger. The mass is changing, volume is not, so therefore the density also increases, according to Avogadro's law. So what does that mean? So far we've seen that the volume is proportional, and this is just to remind you in case you've forgotten, but this little alpha looking sign here means it's proportional. So the volume is proportional to 1 over P, because they're inversely proportional. We also know that according to Charles' law, volume is directly proportional to temperature. And from Avogadro's law, that volume is directly proportional to the number of molecules, which that should be a lowercase n. So when we combine all these together, we get this idea that that V is directly proportional to the number of moles, the temperature, and inversely proportional to P. Well, what we can do to this is give it a proportionality constant. Okay, so that's the same thing as saying V is equal to this constant, which we're going to call it R. That's just a proportionality constant, times N times T divided by P. We can cross-multiply, and when we do that, we get this idea that PV is equal to N times R times T. PV-inert. This is the ideal gas law. PV-inert. PV is equal to nRT. PV-inert. PV-inert. Just keep repeating it. It sticks in your mind, believe me. PV-inert. Okay, so that proportionality constant, the R, is a known it's a known constant. So there are different units that you could use based off of if it's ATMs or we can actually use joules if you want to, or calories, pascals, or torrs. Okay, the two that get used probably the most, from my experience, are these top two. Usually units are either in joules or in liters times ATMs. So almost always we're talking about energy, or we're talking about in terms of atmosphere pressure. Okay, so this is just showing or summarizing what I've already stated. And the important thing here is that we get this equation, the PV-inert equation. Pressure times volume is equal to the number of moles times a constant. You just have to look up the constant on the table, and I would give you the value for R. You just have to memorize the equation. Times temperature. Now please note, this temperature is almost always going to have to be in degrees Kelvin, not degrees Celsius. So make sure that you're always in the correct units. So let's work out an example here. So calcium carbonate, which is a solid, can decompose whenever you heat it up to give calcium oxide solid and carbon dioxide. So a sample of calcium carbonate is decomposed. The carbon dioxide is collected in a 250 milliliter flask. Presumably the flask has a lid on it. After decomposition is complete, the gas has a pressure of 1.3 atms at a temperature of 31 degrees Celsius. So how many moles of carbon dioxide gas were generated? First off, you'd have to look up on a table to see what the rate constant is. And so I've given that to you over here. So R is equal to 0.0821 liters atm per mole Kelvin. So now we have to just write out our table. We have our PV-inert table. I'm not skipping any steps here. Alright, it says a 250 milliliter flask. So which of the variables is that? Well, that's volume. R was already given to us as 0.0821. It's supposed to be 2, 1. Let me write that a little bit better. Liters, ATMs, divided by moles, Kelvin. So that lets us know that immediately we need to convert the volume from milliliters to liters, which would be 0.250 liters. Okay? Also in the problem, it tells us that the gas has a pressure of 1 atm. Well, that specifically tells us that we have 1.3 atm is equal to the pressure, and that's already in the correct units. Like if they had given it to us in torrs or something like that, then we would have to convert it to atms. Okay, and they tell us that the temperature is 31 degrees Celsius. However, we need to convert this into Kelvin, so the way to do that is it's 31 plus 273 Kelvin. So, which is equal to 304 Kelvin. And N is what we're trying to find. So, I'm going to go ahead and erase this part that has the R, so that way we can work our magic, since we have everything in a table now. Okay, so let's go ahead and let's work this out. I strongly suggest that you do the algebra before you start plugging numbers in. You had to memorize p-inert. P-inert. You keep saying it enough, it'll stick. I'm going to change colors that way I can see a difference. We're trying to get the n by itself. Right? This is what we're trying to solve for. So that means we need to divide both sides by RT. So it means PV divided by RT is equal to n. Now we can start plugging and chugging all the numbers in. So we have the pressure, which is 1.3 atms. Times the volume, which is 0.25 liters. We divide that by R, which is 0.0821 LATMs per K moles. And that's multiplied by 304 Kelvin. Let's first check our units. We have an ATM on the top and an ATM on the bottom. A liters on the top, liters on the bottom. This Kelvin will cancel out with this Kelvin. So the only thing that's left whoops, I did not mean to do that, is the number of moles. But since it's on the bottom, the denominator of a denominator, it flips it up to the top. Okay, so we multiply by everything across the top, we divide by everything across the bottom, and we end up with N, which will be in the units of moles, which is important, equal to 0.013 moles of CO2. CO2. I strongly suggest that you, until you feel really comfortable with it, that you make tables like what we have over here on the left-hand side. So let's just review what we've done so far in this talk. First, we went over units of pressure. Most of the time, we're talking about things in terms of ATM, or atmospheric pressure, and or we can talk about millimeters of mercury, which 1 millimeter of mercury is equal to 1 torr. We've also talked about the effects of temperature and volume on the pressure of a gas, or you can think of it about temperature and pressure, or the number of moles on the volume of a gas, and then ultimately we've derived the ideal gas law, which is PV equals nRT. So hopefully this has helped you at least get started with considering the properties of gas, the characteristics of the gas, and the ideal gas law. I will make another video where I just work through an additional problem of using the ideal gas equation.